Hello, so in this video we're going to start looking at how to solve second order ODEs. Now what is a second order ODE? Well, it's just basically the highest derivative is the second derivative. So in other words, we'll have the second derivative, okay, we'll have the first derivative, and we'll have the function, and we'll have some function involving the independent variable, so something, some independent variable, okay, and this, we can always rewrite it so that the second derivative is some function of these other variables. Okay, so that's basically the general form of the second order ODE, right? Now, if we can write, our second order ODE like this. So in other words, we have the second derivative plus some constant, and it doesn't have to be a constant. It can be a variable constant. So, for example, like cos or sine or something like that, times our first derivative plus another constant, again, it can vary, times our function is equal to some function involving t. So, in other words, what we've got there is we can separate, the derivatives and the function and just the independent variables into kind of separate terms, when the highest power is 1, so there's, we're not, say, for example, got that squared, okay, then that's what's known as linear. That's a linear form, okay, so this is what's known as a linear form, okay. If it's non-linear, let me just give you a quick example of a non-linear form. So a non-linear form would be something like this, so y double dash plus y dash times y cubed equals e to the minus t. So why is that non-linear? Well, that's fine. That's linear, because the second derivative is kind of, the highest power which it's raised to is 1. It's not multiplied by anything. But this is where the problem comes. So this is fine as well. But this is where the problem comes. Because what we've got here is we've got the first derivative, okay, multiplied by the function. So that's already a bad thing. We need them to be separate terms. Okay, the first derivative and the functions, they need to be in separate terms. But also, look here, we've got the function being raised to a power which is not 1. Okay, so that's another reason why it's non-linear. Okay, so this is a non-linear function. Okay, and we just have to hope that we can kind of reduce the order or something. And in fact, we solved something very similar. I think it was, that term was ever so slightly different, but we solved something very, very similar in the reduction of videos, in the reduction of order videos. Okay, so basically, yeah. We just have to hope, and I think that was 0 as well, actually. But basically, we just have to hope that we can do something with this to try and solve it. Okay, we won't really dwell too much on non-linear for the moment. Okay, so let's just assume that we've got a linear form. So in other words, y double dash plus a of t times y dash plus b of t, so just constants, coefficients, equals some function involving t on the right hand side. Notice as well there's no coefficient in front of the second derivative. The idea is that if there is a constant, okay, then we just tend to divide through by that constant. So in other words, if that constant was 2, say, then we just divide through all the terms by 2. So in other words, this is over 2, this is over 2, and this is over 2. Well, this is already taken care of. That's already taken care of, already implied in a of t and b of t and q of t. Okay, so basically we always try and make the second derivative monic if it's going to be more useful to deal with it in that form. Okay, now the thing is, if this right hand side is 0, in other words, there's no q of t there, then we call that homogeneous or homogeneous sometimes. So homogeneous, okay, and that is just all it means. It basically means, homogeneous just means kind of one form, okay, and basically if we just set it equal to 0, okay, then it just makes it a little bit easier to solve, and we just call that homogeneous. Whereas if this right hand side is not 0, okay, so basically if we get all the derivatives and the functions on one side, and if we can set this right hand side equal to 0, then therefore it's homogeneous. Whereas if it's not 0, so in other words there is something involving t there, then we call it non-homogeneous or non-homogeneous. Okay, so that's just kind of a little bit of an idea. So basically, once you get all your derivatives and all your functions and stuff on one side, then if the right hand side, what's left on the right hand side, if that's 0, then it's called homogeneous, and if it's not equal to 0, in other words there's some function there, it's called non-homogeneous. Okay, so let's just deal with, for the moment, the case where we don't have variable coefficients, okay, where we just have constant coefficients. So in other words, we have this. So let's say now, for example, I haven't divided through by my, constant at the front, in front of my second derivative. So I've got a constant now, because actually it doesn't matter with the constant coefficient case. We don't have to divide through. So cy equals, let's say, let's actually call it homogeneous. Let's look at the homogeneous case. Let's kind of ease ourselves in gently. Let's look at the homogeneous case now. Okay. Now, at the moment, we're looking at this, and y, so our function, which we, basically the idea is when we're solving any differential equation, the idea is we're trying to find what function for y. So what does y equal? What does y equal? So that when we plug it into this equation, so we find the first derivative and also the second derivative, we plug it into this equation, what function will satisfy that? Well, at the moment, y could literally be anything. It could literally be anything. We've literally got no idea what it is. Okay, so what we have to do is we have to make a complete guess. And in actual fact, I can tell you that a good guess to make is this one. So y equals e to the t, but multiply it by some constant. Let's make it a little bit more tricky. Let's multiply by some constant. So y equals e to the rt, let's just say. Okay, so we have y equals e to the t, and we just multiply by some constant there. Okay. The reason why is because it's a nice thing to differentiate. Y could literally be anything, right? Y could literally be anything. So let's just make a logical guess, and let's just say, well, let's just make y equal e to the rt. In actual fact, this is generally what we do when we've got something like this, and we've got the right hand side is equal to 0. This is generally what we do. It's generally what we do. So we've got constant coefficients, and the right hand side is equal to 0. This is generally what we do. We actually set it equal to that, and there are actually kind of various proofs and various bits of research that have looked into this. But yeah, that seems like a good guess, because this is an easy function to differentiate, right? Because if you differentiate e to the t with respect to t, it just becomes e to the t. So basically now what we're going to do is, this is the reason why we introduce an r, to kind of differentiate, or distinguish, I should say, the function to the first derivative. That's the reason why we got an r, because if we just had e to the t, so just had y equals e to the t, then the first derivative is also e to the t, and the second derivative is also e to the t. Well, that may not be that useful. I mean, it could be that. It could absolutely be that. But this is why we introduce an r. And I mean, there's been a lot of research into this. I mean, I would need a whole new module to kind of try and explain why it is, and I don't think, even then it's been looked into. Things like game theory would look into this. But for the moment, let's just take that because it's an easy function to differentiate. Okay, so let's just go ahead and differentiate it then. So what do we need? Well, we need the first derivative. So basically what we're doing now is we're just assuming that our function that fits this equation is y equals e to the rt. So if we just plug this in there and in there, so basically what do we need? We need the first derivative and in the second derivative. Okay, what's going on? There we go. So we need the first derivative. Well, the first derivative is going to be, it's going to be e to the rt multiplied by the derivative of the power. Okay, that's what we do. So basically, if you have y equals e to the fx, okay, y equals e to the fx, then the derivative of that is the derivative of the power, multiplied by this thing left, this thing left alone, so e to the fx. Okay, so this is what we've got going on here. Okay, the derivative of rt is just r. Okay, so that's why it's multiplied out the front. This is just by the chain rule. Okay, and so again, the derivative of this thing, so the second derivative will just be the derivative of this thing. So we've got an r. Okay, and again, we just know what that is. Well, it's just, so we know what the derivative of e to the rt is. It's that thing. So in other words, we get r times r e to the rt, which we can just simplify down as r squared. Okay, oops, r squared. Right. So in other words, now when we plug this thing back into this, in other words, y goes in there. Okay, y dash goes in there, and y double dash goes in there. Okay, then this is what we end up with. We end up with a y double dash, which is that thing. So a r squared e to the rt. Okay, plus, so that's that thing dealt with. Then we just plug that thing into there. So plus b y dash, which is r e to the rt. Okay, so that's that thing dealt with. And then we're just left with cy. So plus c times that thing. So c e to the rt, and that's all equal to 0. Oops, where have we gone? So that's all equal to 0. Okay. So basically, now what we just do is we can do a little bit of rearranging with this, right? We can just take out an e to the rt. Yeah, because there's an e to the rt there, there's an e to the rt there, there's an e to the rt there. So let's just take out e to the rt. Okay. What we left then, we've taken out an e to the rt, so we're left with ar squared. Okay, plus br plus plus c. Okay, and that's all got to be equal to 0. So this is the same thing. Well, e to the rt, where are we going? E to the rt cannot be 0, right? E to the rt cannot be equal to 0, because basically what we're saying here is that what do we have to raise to the power of e to make it equal to 0? We just know by the power laws that we can never get a 0th power. Okay, so what times by itself many times, apart from 0, of course. But we know that e is not 0. Okay, so e raised to e multiplied by itself how many times will equal 0? Well, it never will. It can equal 1 if we raise it to the power of 0, but it will never equal 0. It will never go negative. So therefore, we know that e to the RT is non-zero. So in other words, we've got two things which are being multiplied together. We've got e to the RT times by that thing, and it's equal to 0. Well, if two things multiplied together equal 0, then we know that one of them has to be 0. And we've just established that e to the RT cannot be 0. So in other words, what that means is that this thing in the brackets here, so in other words, AR, this should be AR squared, because from there, AR squared plus BR plus C, that must be equal to 0. Okay, and what we've derived there is something called the characteristic equation. What we've derived there is the characteristic equation. And, this is fairly easy to see. You don't have to go through all the steps each time, but this is where it kind of comes from. Because if we just compare the two, so if we just compare the two like this, okay, you can see here, if we just compare those two terms, the highest derivative is the second derivative. Go away. Highest derivative is the second derivative. The highest power of our r, if you like, is the second power, okay? Then if we just compare the second term, so these two things, okay, highest derivative in there is our first derivative. The highest power in here is, if you like, our first, our highest power is a 1, okay? And if you look here, the highest derivative, the last term, is, if you like, our 0th derivative. Okay, this is raised to a 0th derivative. If you like, the 0th derivative of something is just the function itself. And if you like here, it's got r to the power of 0, which we just don't bother really writing. So basically, this is how we can convert homogeneous differential equation, second order linear differential equation, into its characteristic equation, okay? And the reason why this characteristic equation is good, well, essentially what we want to do is we want to try and find, we've assumed that this thing here, this equation here, has a solution which looks like that, okay? So in other words, we know what, t is a variable, y is a variable, and we also know that, we know what e is, it's a number, right? So in other words, we want to find out what r is. And we can find it by solving this characteristic equation. Okay, so to try and find r. So in other words, we solve it by finding the quadratic formula. So r equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that's a good place to start. Now you may say at this point, well, hang on a minute. We've assumed that the function looks like that. It may not. Well, the thing is with differential equations, okay, I can't prove to you why that should be the case. I can show to you that it works, but I can't prove to you that it should be the case. Okay, like I say, it takes a lot of proof. It takes a lot of kind of things like game theory to try and prove that is the solution. And sometimes with differential equations, we just have to. The best thing we can do is just guess a solution, guess a form. We kind of have to look at the differential equation and see, well, it makes sense just by, we kind of recognise that when we have a differential equation of such and such a form, we know that to try and, we try a solution of such and such a, looks like something, such and such a form like that. So in other words, when we see an equation that looks like something, we see an equation of a certain form, we know, oh, right, that means that we have to use that solution, okay? And essentially, it's just glorified trial and error. That's how we know that is actually the solution. So I can't show you that is the case. I can show you that it does work. I can, when I get to the answer, I can say that works. And you may say, well, that's just blind luck. But actually, no, this is kind of what you have to get used to with differential equations. That, there's no kind of analytic or algebraic way of deriving this. You just have to kind of guess it as such. And the reason why I just have to guess it is because you've not just got a derivative, because you've got derivatives, it's not just a function, okay? But usually with just a function, you can solve it sort of algebraically quite happily. But here, because you've got derivatives as well, it becomes a little bit more tricky. So that's why you just have to guess a form. Okay, so in other words, we want to find what r is. So r equals, you basically solve this, okay? And you can have three different cases. You can have the first case, so case one, which is when you end up with two roots, obviously. You'll end up with r1 and r2. When you solve a differential equation, it's a quadratic. Oh, sorry, don't solve it. differential equation. Solving a quadratic, you know, solving this thing. When you solve a quadratic, okay, you get two roots out. The first case is when R1 and R2 aren't the same. So they're not the same, but they are real. Okay, so they're, you know, you might call them distinct if you like. Distinct just means different. Okay, so they're not the same, but they are real. Okay, and then when that's the case, we look for a certain type of solution. Okay, and I'll come on to that in a moment. The second case, okay, is when R1 is the same as R2. So in other words, we get two equal roots out, but they are still real nevertheless. Okay, so we get two equal roots out. All I'm doing now is, you know, if you remember way back to A level, you just look at this discriminant to determine which type it is. So if the discriminant, if b squared minus 4ac is greater than 0, so in other words it's positive, then therefore you get case 1, where you get two real roots. Okay, if this thing is equal to 0, so b squared minus 4ac is equal to 0, then, you know, effectively that just disappears, and what you're left with is minus b over 2a. Okay, and you get the same root, so R1 equals R2, so you only get one root. And the third and final case, at A level, we just said, oh, you know, there's no real roots. But here we have to, you know, we're grown-ups now. We just basically say that R1 and R2 are just complex roots. Spell complex roots, and that's basically where the discriminant minus b squared minus 4ac is less than 0. Okay, so those are the three cases, and those are the three cases that we're now going to come on to consider, and we're going to consider each different type of solution for that. So let's consider the first case then. So this is the case when these two roots aren't real. They're real, but they're not equal to each other. So in other words, remember what we guessed. Remember we guessed a solution of the form y equals r to the t. Okay, so we guessed a solution of this form, y equals r to the t. And basically what we're after is we're trying to find out what r is. Well, we've got now two values for r. We've got so we've got y equals e to the r1 times t, and we've got y equals e to the r2 times t. So let's kind of, you know, these two things are going to be different. You know, that's going to be different to that fairly obviously. So let's call this solution 1. Let's call this solution 2. Okay. Well, basically we can still have both. We can have those two things. Okay, so we've now got two solutions to our original differential equation. We've got two solutions to our original differential equation. Remember what our original differential equation was? It was a y double dash plus b y dash plus cy equals 0. So in other words, what we're saying is that we can have two solutions. Either one of these will work. But what we can also do is we can come up with a more general solution just by putting these two things together. So in other words, we can say our general solution, y, will just be this thing, e to the rt, so r1 times r1t, okay, plus this thing, so e to the r2 times t, okay. And this is what's known as a linear combination. Now, a linear combination is just basically where we just, you know, this is solution 1, this is solution 2. We just add the solutions together. We don't raise them to any powers, which is what makes it linear. And we just add the two things together. So we just come up with two terms. We put them together just by adding them together. And that's what's known as a linear combination. A linear combination. Okay, well, the nice thing about a linear combination is it basically says that we can multiply it by any constant value, so any kind of number we like. So let's just call it constant 1, and let's call this one constant 2. We can multiply our two solutions by any constant value we like. We can't multiply them by any kind of variable function, so we can't multiply them by a coefficient that's dependent on t, say, but we can multiply them by any number we like, and it will still be a general solution. That's kind of the nature of a linear combination. And kind of we'll come on to hopefully building up the intuition behind that a little bit later on with linear systems, where we come up with things like eigenvectors, which you know, are basically using these linear combinations, and hopefully you can see it a little bit more graphically. But just to kind of give you a brief idea now, if we have an eigenvector corresponding to this, say, you know, just a vector, say, if we want to draw this solution on the graph, well, basically we can have any multiple of that solution. So say if e to the r1t is just well, actually no, let's not use vectors because that might confuse you. But it's going to look something like that. Okay, it's going to be a graph that looks something like that. Well, basically we can have any multiple of that graph. Okay, it will still be a solution. So in other words, we can stretch that graph any way we like, and it will still be a solution. Okay, so that's essentially all that's going on. So basically, you know, this is the general form. Oops. Gone up, touch the cursor. So this is basically the general form when we have two distinct real roots. Okay, so we look for something like that, right? So let's look at now case 2. Okay, so case 2 is when the two roots are equal. Okay, so they're equal roots. In other words, they're the same thing. So we're basically, you know, we can have, if you remember our original solution, it's y equals e to the rt. Okay, so in other words, what we're saying is that, you know, we can have a solution y equals, so let's call it y1 equals e to the r1 times t, r1 times t, and y2 is e to the r2 times t. Okay, so what we're basically saying there is that, you know, what we're basically saying there is these are the solutions that we form. So basically just by putting r into you know, putting r1 into that thing and r2 into that thing, we get our two solutions out. But look, we've said that r1 is equal to r2. So in other words, if r1 is equal to r2, then what we're basically saying there is that y1 is equal to y2. So we're basically saying that we only get one solution. Well, that's not really good enough with differential equations. What we need to do is we need to try and distinguish. We need to try and distinguish between these two solutions. You know, we should get two solutions out. This, the highest order, you know, the highest order of our differential equation. So we have a1 double dash plus by dash plus cy equals 0. Our highest order is the second derivative. So what we're basically saying is that we should have two solutions, or, you know, when we have our general solution, we have it consisting of two terms. So in this video, we're going to kind of... So basically what this means is the second order, the second derivative, we should have two solutions in our general solution. Okay, so in other words, we should have our y1 and we should have a y2. But at the moment we're saying, well, the two things are the same. Okay, so in order to stop them kind of being condensed into one, what we basically do is we multiply one of them by our independent variables. So in other words, what are, you know, the variable that we differentiate with respect to. So we've got y is a function of t, so therefore our independent variable is the t. Okay, it's the variable that that we've got in our function. Okay, so we just multiply it by t. So say, for example, if this was an x, this was an x and not a t, this was an x and not a t, then this would be x down here as well. Okay, but, you know, basically this is the idea. So we can now distinguish between the two. It kind of separates the two and stops them becoming together. Okay, so it just very, very subtly alters them. Okay, so now our general solution is this solution, so e r1t plus this solution plus t, now e to the r2t, and remember it can be a linear combination, so we can have any constants we like, any sort of numbers we like, multiplying through them. So that's the general solution for the case when we've got a real root. Okay, so let's look at the third. So this is now the case when r1 and r2 is complex. Remember how we got r? Okay, so we got r by having the minus a plus or minus, we've used this quadratic formula, right? Minus 4ac all over 2a. Okay, so in other words, what we're saying now is that this thing is going to be negative. In other words, it will lead to a complex number. It will lead to a complex number. So, you know, if we just now take, it'll be a complex number. So in other words, when we take the modulus of that and multiply through by I, then basically what we'll end up with is that R1 is going to be, you know, some complex number. Let's call it alpha plus beta I. So in other words, you know, this thing plus this thing now. Oops. This thing now. So, you know, it will come clear when we do examples. So in other words, we're using the plus of the square root. Okay, and R2 is the same thing, but using the negative of the square root. Okay, so it's equal to alpha minus beta I. And so basically, you know, when we're finding the two roots of a quadratic which have complex roots, they should be conjugates of each other. They should be conjugates. So one should be a plus and one should be a minus. That's what we mean by conjugates, and everything else should be the same. Okay, so the thing in between the imaginary and real parts should be, one should be plus, one should be minus. That's all conjugate means. Okay, so we've got two conjugates now. Okay, well, remember what our solution was. It was y equals e to the rt. So in other words, when we put, you know, the first solution that we're going to get out is just r1. So it's going to be e to the r1, which is alpha plus beta I. Okay, and the second one is when so y2 is going to be using r2, so e to the, sorry, that should be times t as well. My apologies, that's r1, so that's r1 in there. Okay, I've just simply substituted that in, and I've got to keep the t in. Okay, and then we've still got r2, so r2, which is now that thing there, so it's alpha minus beta I times t. Okay, so let's do a little bit of work with these two things. So we've got y1, let's work with y1 first of all. y1 equals alpha, I'm going to multiply through by t. Okay, so alpha t plus beta t times I. Okay, so beta t times I. Well, okay, and the same thing for y2 then. So y2 is equal to e to the alpha t, just multiply through by I t, minus beta t times I. Okay, so remember when just by power laws, effectively, when we've got two things added, when we've got powers where we've got two things added together. Say, for example, if we have, let's say, for example, we had 2 to the 3 times 2 to the 5. Okay, well, that's just the same thing as 2 to the 3 plus 5. So we've got the same base. Okay, and we just add the powers together. We're going to do the same thing now, but just in reverse. Okay, so this is going to be equal to e to the alpha t. So I just split this up into two individual kind of indices. So e to the beta t times I. Okay, so I've just split that up into two things. I'm going to do the same thing for y2. This is going to be e to the alpha t. Now here I'm going to be a little bit sneaky. So it's going to be e, but I'm going to make it minus I. So I'm going to change this to a plus. I'm going to change this to a plus and this to a minus I. So it's still going to be the same thing. But I've just put the minus times by the I instead of where the plus is. So it's going to be to the beta t times minus I. Okay. Now, can you remember Euler form? This is going to be a real number, by the way, because alpha and t are both going to be real numbers. So we're still going to get e to the alpha t. Okay. Can you remember Euler form? So in other words, if we have a complex number written as this, e to the I theta, that's just the same as cos theta. So we basically use this angle, this theta here, to be our argument inside our trigonometric, plus I sine theta. Okay, and that comes from kind of working through power notation. Effectively, there's plenty of proofs probably on there. If not, there are some proofs in the lecture notes of kind of, where that comes from and trying to prove it and stuff. But basically, we can now say that e to the beta t times I, so in other words, theta is now beta t, so theta is now beta t, okay? So this is now times then cos, well, what's my theta? It's now beta t, okay, beta t plus I times sine of my theta, which is beta t, okay? So that's now the thing for y1 now. I've lost a little bit of space, so let me just try and make this a little bit smaller perhaps. So I can write a similar kind of thing out for for y2. Okay, so now y2, what will that be? It'll still be e to the alpha t, because that's just a real number. That will just come out as a number, right? Okay, times this thing. So it's going to be cos beta t. That's now my theta. Beta t is still my theta. Okay, but this time, because I've got a minus here, I'm just going to replace this by a minus. So minus I. So before I had a plus I, if you like. Before I had a plus I, which is why I've got a plus I in there. Okay, now I've got a minus I, so I'm going to write a minus I in there. Okay, that's not really a strictly speaking mathematical argument. This is now sine beta t, by the way. That's not strictly speaking a mathematical argument, but it works. They should be conjugates of each other, because this should be the conjugate root, so therefore this minus I should mean that we've got a conjugate going on, so conjugate to this thing, so therefore the plus should become a minus, just like it should do in the ordinary conjugate, because this is now my real part and this is my imaginary part. So this is the plus, this is my real part, this is my imaginary part, so this now should become a minus if it's going to be a conjugate. Okay, it's kind of a very weak mathematical argument, but if you follow that, it does work. Okay, so let's now get rid of that. So these two things now are going to be my my y1 and y2. So in other words, when I write y, it's going to be y1 plus y2. Okay, I don't have to put coefficients in there because it's just going to get in the way. I can put coefficients in there if I want. So otherwise I can put c1 y1 plus c2 y2, but I'm going to actually omit them. I'm going to leave them out for this video, just purely because they're just going to get in the way. And actually, if you just kind of evaluate this, you could equally put a minus in here. That's absolutely fine, but we're just going to leave it for a plus for the moment. But actually, when you evaluate these two things, so in other words, when you do that plus that, what we quite often find is that you end up with a cancellation term or something. I mean, we're going to do an example on it, but this is just kind of the general form of the answer. So basically, the general form of the answer should be the two solutions added together.